Here we're going to talk about a variation of the alkene halogenation. So before we worked with an alkene and added a halogen like bromine, and it added Br to each carbon of the double bond. Now what we've done is we've added a solvent. A lot of times when you have a solvent, it'll be written under the arrow. In this case it's water, but what you should recognize about water is that we have oxygen, we have the lone pairs. This is a nucleophilic solvent. So what that ends up doing is it takes the place of the bromide that attacks in the second step. So in the products, we're going to end up with two stereoisomers. And you can see that we've added something across the double bond, but now we've added a Br and an OH, and the OH came from the water. They're still opposite, they're trans, and we end up with the two stereoisomers. So we have one where the bromine is out and the OH is back. We have one where the bromine is back and the OH is out. So let's label these. I'm going to make this first one, we'll just call it product A, the second one product B. And we're going to look at the mechanism and talk about how we get these products, and also why don't we end up with the bromine at this more substituted carbon. It selectively goes to the less substituted carbon, and the OH is on the more substituted carbon. So in the first step of the mechanism, it's just like you learned before. We're going to react this alkene with the halogen. We have Br2. I'm going to draw the lone pairs on one of the bromines. And for this step, we use three curved arrows. One, we go from the double bond to the first bromine. We lose the second bromine as a leaving group, and then use a lone pair of this first bromine and come back and attack one of the carbons of the double bond. It really doesn't matter which you do in that case. From here, we're going to end up with the bromonium ion intermediate. When we draw this, we want the bromine to be on dashes or wedges. So let's say we do the wedged product. We need to make both bonds to the bromine a wedge, because with this three-membered ring here, it's impossible to have one wedge and one dash to the same atom. If that's the case, this methyl group ends up going to the back. Now, of course, that bromine could have come in from the back side of this double bond to give you a stereoisomer intermediate. And that will put the bromine back. We also have our leaving group that left, the Br minus, so I'll draw it as just a third piece. Now, what we did previously was we would then take this bromide as a nucleophile and add it to the bromonium ion and open that up. The difference now is we have this nucleophilic solvent. And relative to this bromide ion, there's a bunch of solvent. There's a ton of solvent that completely overwhelms the reaction. Think of it like this. If you were to dump 100 golf balls into a swimming pool, think of the bromide as the golf ball. And then think of your hand as the bromonium ion. So if you take your hand and put it down in the swimming pool, are you more likely to run into one of the golf balls, or more likely just to grab a bunch of water? It's the same thing. There's so much water around that it completely overpowers the bromide ion, and probability-wise, it's more likely for the water to run into this electrophile than it is the bromide. So when we do that, let's look at the two pathways. So if the water adds to this first bromonium ion, it's going to add as a nucleophile, and it selectively adds to the more substituted carbon. And we'll talk about why that is. It adds there. It comes in from behind the leaving group, which is a bromonium ion, and opens that up. When you do that, we now have the Br attached here on the wedge. The water comes in from the very back, so it ends up on the dash. And we still have the 2 hydrogen on the oxygen. And because it comes in from even further back than this methyl group, as it comes in, this methyl group gets pushed out to the front. So I'll put the methyl on a wedge. So we get this intermediate, and now to get to our final product, we just need to get rid of one of the hydrogens on the oxygen. You can use another molecule of water, or I'm going to be very generic and write B with a lone pair, saying anything with a lone pair in my reaction mixture can do this. So it'll come in, take one of these protons off of the oxygen, and now we're left with the neutral product, and that's product A. Now, if we do the same thing with our other stereoisomer, I'm not going to draw out all of the steps this time, but if you add the water, that water will add from the front side again to this more substituted carbon, and the product you end up with in the end will have the bromine down here back, the OH right here out, and this methyl group will end up back. And that's product B. So a couple of features with this. The solvent, which in this case is water, takes over the bromide as the nucleophile. The solvent attacks the more substituted carbon of the bromonium ion. So that is this carbon here in each case. And finally, the nucleophile or solvent water adds to the side opposite the leaving group, and the leaving group is the bromonium ion. Now let's talk about why the water, or whatever your nucleophile is, attacks the more substituted carbon of the halonium ion. So if we look at the intermediate we did in the last example, and I'm not going to draw in stereochemistry because it's not really necessary for this discussion. Here's our bromonium ion, and we know that the nucleophile attacks this more substituted carbon. And as you think about sterics, that doesn't necessarily make the most sense because this seems like a very hindered site compared to the more open site here. But what you need to think about is the fact this is an electrophile with a bunch of positive character. And think about the hypothetical. This doesn't happen, but what if this actually broke open like this? Let's draw what we get. We get a carbocation. Now let me redraw this, except this time we're going to look at the hypothetical of breaking open the bromonium ion on the other side. When you do that, you also get a carbocation. Like this. Now you know about carbocation stability, and we know that this one is secondary and this one is tertiary. This one is more stable. Now this step doesn't really happen mechanistically, but what it tells us is that this particular carbon has more positive character than this carbon because it's more substituted. We know positive charge on a more substituted carbon is more stable. Therefore, this carbon can better handle positive character. And what that tells us, more positive character means it's more attractive to a nucleophile. Because a nucleophile is negative and it's attracted to the most positive site. So again, keep in mind, this doesn't actually happen as far as breaking open the bromonium ion first, but it does explain why we get this type of character. So I'll just make a note here for you, just so you know that these aren't true intermediates you get in the mechanism. So if you're drawing a mechanism, you should not be drawing these carbocations.